Welcome to the lucky episode number 13 of my exercise series Introduction to Physics. Today we are going to talk about gravitational fields. Gravitation is all around us and yet it's sometimes actually hard to grasp. So let's start easy. We are starting really with the basics and then work ourselves up. So let's get on with it. Task A. Derive a general relationship for the orbital period and the orbital velocity of a satellite in a circular orbit around the Earth, if the height h of the satellite, the gravitational acceleration g on the surface of Earth, and the Earth radius r are known. B. Calculate the first cosmic velocity v1 and the associated orbital period t1 directly on the Earth's surface for r equals 6,378 kilometers. And C. Can one deduce the mean density of Earth from the orbital period t1? So the variables h, g and r are considered to be given for the first part. Of course, we know that g, the gravitational acceleration on the surface of Earth, is assumed to be 9.81 meters per second squared, and the radius is given as 6,378 kilometers. We are searching for, in point A, the time t and the velocity v of the satellite depending on h, g and r. In point B, we are searching for v1 and t1, and in point C, we are looking for the density as a function of t1. So let's make a sketch. We can see here the Earth. We can assume it's spherical in shape and we know the radius r. In a height h above the surface of Earth, we have given a satellite that is moving at a constant velocity in a circular motion. So how do we solve our problem? Well, when the satellite is moving around Earth, of course, the direction of its motion is constantly changing. However, it's going to move at a constant velocity. And the force that is dragging it down to Earth, which is the gravitational force, is at equilibrium with the centrifugal force that's moving it away from Earth. Hence, Fg, the gravitational force, equals Fc, the centrifugal force. How are they calculated? Well, Fg equals gamma, the gravitational constant, times the mass m of the object, in our case the satellite, multiplied with the mass m of our central body, which is the Earth. Hence we take an uppercase M for that. And we have to divide this product by the distance squared. And distance means we are talking about the distance of the satellite to the center of rotation, so the center of Earth. On the right-hand side, we have the centrifugal force, which is m multiplied with omega squared and again distance d. So the distance d is simply radius of Earth r plus height h above Earth. Omega is the angular velocity of our satellite moving around Earth, and we can calculate it simply from 2 pi, which it takes to go around the planet once, and divide it by the time t that it takes. And finally, of course, the gravitational constant gamma is, as the name suggests, a constant, and it's equal to 6.674 times 10 to the power of minus 11 meters cubed per kilogram and per second squared. Hence, we have on the left-hand side gamma multiplied with the mass m of Earth divided by r plus h squared. The mass of the satellite is really not important because it cancels out. And on the right hand side we have 4 pi squared divided by t squared multiplied with r plus h. And we are actually looking for the time t that it takes to move around Earth. So let's take t on the left hand side and all other variables on the right hand side. Then we have t squared equals 4 pi squared divided by gamma m multiplied with r plus h to the power of 3. And well, gamma and m are unknowns. We are supposed to calculate t as a function of r, h and g, the gravitational acceleration on the surface of Earth. So how do we get this? Let's think about it for a moment. What do we know about the gravitational force on the surface of Earth? Yes, we can calculate it with exactly the equation we've seen before. Gamma multiplied with the mass of the satellite multiplied with the mass of Earth divided by the distance of the satellite to the center of Earth, which is, if we're talking about the surface of Earth, the radius squared. And of course, this is not standing alone, because on the surface of Earth, we can actually describe the gravitational force really in a simplified way, because it's nothing more than mass m of the object, the satellite, multiplied with the gravitational acceleration g on the surface. And yes, again, the mass m of the satellite cancels out, and hence the product gamma m equals gr squared. So we can put this simply in our equation in order to calculate our time t. And what we get is that t squared equals 4 pi squared divided by g and r squared multiplied with r plus h to the power of 3. Now, of course, we want to calculate t, so t equals 2 pi multiplied with the square root of r plus h cubed divided by g and divided by r squared. In addition, we were looking under point A for the associated velocity of the satellite. Now, this satellite is going to follow a uniform motion. Of course, the direction of this motion is changing constantly. But apart from that, it's a uniform motion where we can calculate the velocity as change in distance divided by change in time. So delta s divided by delta t. And the satellite, in order to go around Earth in a circular fashion once, it's going to travel 2 pi times the distance, and the distance is r plus h, divided by the time that it needs, which is actually our uppercase t. And this makes it really easy to solve this part of the problem, because we've just calculated t, or we've derived t to be more precise. So we can substitute t here, and what we get is that v equals 2 pi r plus h divided by 2 pi multiplied with the square root of r plus h cubed divided by gr squared. Well, that looks still a bit chaotic, but come on, we can simplify it. We see already that 2 pi cancels out on the right hand side, and we can even go ahead, and what we get is that the velocity of the satellite is actually the square root of g r squared divided by r plus h. Up until now, we haven't actually been using, actual values. This comes now in the second part. We are supposed to calculate the first cosmic velocity. And the first cosmic velocity, v1, is the velocity for h equals 0. Which means that we can just take our equation that we've just derived and substitute h by 0. Hence, we get that v1 equals the square root of g times r. And we can simply take our values and put them in a calculator, but be very careful, because as you can see here, g is given in terms of meters per second squared, whereas the radius was given in terms of kilometers. So this is actually the first task in this series, Introduction to Physics, where we haven't recalculated our initial values into their basic units. As a result, we have to be careful at this point, and actually when we put it in a calculator, we have to multiply the 6,378 kilometers with 1,000 in order to get meters. But if we do this and put it in a calculator, what we get is that V1 equals 7,910 meters per second, which is actually 7.9 kilometers per second. So whenever you do something like this and you do not recalculate your units initially, be careful with the units at this stage. What does this mean, 7.9 kilometers per second? Well, it basically means that with the first cosmic velocity, a body describes a circular orbit around the Earth and becomes a satellite, if it is started at this velocity. With a somewhat higher velocity, an elliptical orbit is reached. Now, of course, if our satellite travels with 7.9 kilometers per second, each second, how much time does it take to turn around the Earth once? In order to calculate this, we have actually given the exact equation. We know that t1 equals t if we substitute the height h by 0. And if we do this, we get that t1 equals 2 pi multiplied with the square root of r over g. And also here we can take our values that were given, and again we have to be careful with the units, so we have to multiply our radius r with 1000 again, and what we get is that t1 equals 5066.3 seconds. Now, I suppose not everybody has a grasp of what 5000 seconds are. So let's recalculate them, and what we get is that t1 equals 1 hour, 24 minutes and 26 seconds. Are we done yet? No. There was one last question, whether the mean density of Earth can actually be calculated from t1. How do we approach this problem? We know that in general the density of an object is mass of the object divided by its volume. In our case we have the mass of Earth, m, and we are going to divide it by its volume. Assuming that the Earth is of spherical shape, the volume of a sphere equals 4 over 3 pi r cubed. And yes, we have given r cubed, but this is actually not the question. We are supposed to substitute it by t1. And, well, there is an m, the mass of Earth, and r cubed, and we somehow have to make this t1. What do we know? Well, we can actually substitute the mass, because we've seen before that the product of gamma and m equals g r squared. So let's substitute the mass m right away. Then we get that the density ρ equals 3 times g times r squared divided by 4 pi gamma r cubed. Or in a simplified way, ρ equals 3g divided by 4 pi gamma r. But this is still not helpful, right? Because there's still no t1 in this equation. Just as a reminder, what does t1 look like? Well, t1 equals 2 pi multiplied with r over g. Wait, if we're looking up here for ρ, we see that ρ contains g over r and t1 contains r over g. So let's divide t1, the whole equation of t1, by 2 pi and then square it. What we get is that r over g equals t1 squared divided by 4 pi squared. And yes, if we turn this equation around, we can actually put it into our equation for the density. And what we get is that rho equals 3 divided by 4 pi gamma multiplied with 4 pi squared divided by T1 squared. And after simplification, we get that rho equals 3 pi divided by gamma T1 squared. Which means, yes, the mean density of Earth can be deduced from the orbital period T1. Of course, assuming that we know the gravitational constant gamma. I think this is really an interesting point. Making a couple of simple assumptions, we can actually calculate the average density of our planet from the orbital period T1. This is really fascinating and I hope it helped you, and if it did, consider subscribing, give me a thumbs up and let me know your opinion in the comments below. If you have questions, just type them down and I hope to see you soon for another video. Bye!